So let's say we wanted to graph something like f of x equal to 4 to the x. Well, really, when I think about this graph, I think about it being exponential, and I know the basic shape of it. So this is going to look like this. It's got your usual exponential shape. You might plot a few points. I probably wouldn't. If I was going to plot some points, I would definitely plot that one, 0, 1. And I might plot like one more point, say 1, 4. To me, that's probably more points than you really need. As long as you've got the basic shape, that's really all that matters. So let's look at a couple transformations. What if I wanted to instead graph 4 to the negative x? Well, that's going to reflect the graph across the y-axis. So we're going to get the same y-intercept, but it's going to look like this. And again, if I were plotting some points, I would still have the point 0, 1. And it's kind of nice to see here that instead of x being 1 and y being 4, x being negative 1 is going to give us a y value of 4. Because if x is negative 1, then you're going to get 4 to the negative 1, which is 4 to the first. 2 more transformations. If we wanted to graph, say, y equal to negative 4 to the x, the way I always kind of think about these things is if you do something kind of to x first, it affects the graph in a horizontal way. Whereas if you do something to kind of on the outside of the function, it affects the graph in a vertical way. So putting this negative sign on the x flips the graph horizontally. Putting the negative sign outside the function flips the graph vertically. It's going to look like this. You're going to get the point 0, negative 1, right? When you plug it, so it's kind of important to see here, and this is where things are getting a little bit off. Let's see if I can. It's really kind of. Sorry, 1 second. I'm trying to make sure that everyone can see all the things. I know it's like the Blair Witch Project over here, trying to get this camera to look right. Sorry, 1 sec. Really would like you to look better. Why is it so off? 1 moment. Sorry, guys. Just would like this to look not terrible for you all later. Okay, I think that's about as good as we can get. Okay. So if we were to plug in 1 for x, sorry, 0 for x, so if x equals 0, y is going to equal negative 4 to the 0. And when we see that there, it's important to remember that the power part happens first. So we do 4 to the 0, which is 1, and then we get negative 1. And then lastly, let's look at what happens if we shift it, say, down. So I wanted to graph 4 to the x minus 2. This is kind of, in my opinion, one of the more interesting transformations, because if you shift this thing down 2 from its original graph, we get some new points. We get some new features, actually. So if you shift it down 2, the horizontal asymptote, which was 0 for each of these previous graphs, the horizontal asymptote now is going to be y equal to negative 2. And the new y-intercept is going to be y equal to negative 1, because we took our y-intercept of 1 and shifted it down by 2. And what's kind of different about this graph versus all the other graphs is it also has an x-intercept. And typically, if I'm graphing a thing, I usually like to find intercepts. So to find the x-intercept, well, we're going to find the x-intercept the way we always find the x-intercept, by setting y equal to 0. So then if I'm going to solve 0 equal to 4 to the x minus 2, I'm going to bring the 2 to the other side. So I'm going to get 2 equal to 4 to the x. And then you can kind of either know the answer or solve it by writing both things as powers of the same base. So I might rewrite this as 2 to the first equals 2 squared to the x, or 2 to the first equals 2 to the 2x. And then once those things are the same, I should say once those bases are the same, then we can set the exponents equal to each other. So 1 equals 2x, which means x equals 1/2. And that is your X intercept, 1/2, 0. So that's how I would graph that one. And I know the chat went away, sorry. Cool. So these are some pretty basic transformations of graphs. Questions? Questions from Zoom? If you guys can't see anything, or if you're like, if there's anything you want to know more about, just let me know. And it feels like I would love for you to see my face. Let me do one thing. Let me see if picture in picture is going to be terrible or not. Where's it? It's not terrible if like it actually gives me the camera. Sorry, one sec. Yeah, but that's not what I want. I want the picture in picture. There's a lot of me. He was like, I know that's not what you're looking for. Let's try that again. Oh, I see. Okay, I get it. All right, here we go. Cool. So let me see if I can move this just that way. Nope, that's gonna cover that. It's always a challenge. Okay, I think I might have found the sweet spot. A little bit to the right. But now I'm covering up the other thing. I just do this. We'll get this worked out. Still the first week. Yeah, it's hard making these both look great. Okay, I think we're good. Again, if there's something you can't see, just let me know and I will try to either explain or make it more visible. Let's do the same sort of thing for logarithmic graphs. So let's talk about graphing the natural log of x. So y equal to the natural log of x, which I'll remind you is just y equal to log base e of x. We're never going to write that. We're always going to write this, but it's good to know that they really mean the same thing. It's just an abbreviation. So the graph of this looks like this. Has an intercept of 1, 0. And I should remind you that this is the inverse function of y equal to e to the x, which I know we mentioned last time, but it's worth mentioning again. So here's good old e to the x. It has your basic exponential shape. And these two graphs have kind of all the opposite things, meaning for y equal to e to the x, just a few things we mentioned last time. The domain is everything. The range is all positive numbers and it has a y-intercept of 0, 1, has a horizontal asymptote of y equals 0. Welcome, come on in. Oh, I forgot to check symptom surveys. It's like a huge deal, but I'm supposed to do it. So you're like, yeah, I know. Thank you, appreciate it. Thank you, appreciate it. For all 2 people that are here. Lots of people on Zoom. Zoom people obviously don't have to check your symptom surveys. Versus y equal to natural log of x. Check out how all the x and y things interchange. So for the natural log of x, the domain is all positive numbers. The range is everything from negative infinity to infinity. Instead of having a y-intercept at 0, 1, there's an X intercept at 1, 0. Literally, the X and Y coordinate have interchanged. And instead of having a horizontal asymptote at Y equal to 0, there is a vertical asymptote at X equal to 0. So inverse functions always kind of have this relationship with each other where if something is true for one function, the kind of inverse thing for X and Y is true for the inverse function. It's kind of neat. And then we could graph some shifts or transformations of the natural log of X. So for example, if I wanted to graph Y equal to the natural log of X plus 3, I know I've added 3 on the inside, so I'm going to shift 3 to the left, but the easier way for me to honestly think about this is just to think about the domain. So here, the domain, I know that the insides of a logarithm have to be positive, which means in this case, X has to be greater than -3, which also means my vertical asymptote is going to be where X is equal to -3. It's kind of the place where if you plugged in that number for X, you would be trying to take the natural log of 0. So graphically, I'm shifting 3 to the left. That's where my new vertical asymptote lives. And then it's going to have the usual shape. How did I know it went through that point -2, 0? Well, because my X intercept also shifted 3 to the left. So my previous X intercept was 1, and I went 1, 2, 3. Oh, it's going to be -2. So X intercept is -2, 0. Here's my graph. Not anything really special about it. There it is. Let's look at one more example. Let's graph Y equal to the natural log of 4 minus X. And to be honest, this is always the kind of combination of a shift and a reflection that always throws me off. I'm always like, oh, do I shift left? Do I shift right? I know I'm going to reflect it. Here's what I would really say. Again, let's look at the domain. The domain is the easiest way to figure out how the natural log graph kind of looks. So I know my domain has to be where the inside part of the logarithm is positive. So solving for X, I can just add X to both sides and say 4 is greater than X, or if you prefer, X is less than 4. Same deal. Well, great. That really helps me because now I know that the graph has to live to the left of 4. And that my vertical asymptote is going to be at X equal to 4. But now it's not going to have what I would call the typical logarithmic shape because it's going to be going up and to the left instead of up and to the right because we know it has to be right on this side because X is less than 4. So it's going to do this kind of deal. I'm never good at graphing these. And that's all right, but it could be better. So there's my logarithmic graph there. It definitely got an intercept of 3, 0. If I didn't just know that was the intercept, how would I find it? Well, how do we usually find an X intercept? We set Y equal to 0. Oh. We set 0 equal to the natural log of 4 minus X. We can solve that by rewriting it as an exponential equation. We can rewrite it as e to the 0 equals 4 minus X. And then 0 is 1. And if 1 equals 4 minus X, we're going to get X equal to 3. Oh, sorry. Just can't quite see that there. Yeah. Sure. So there's actually kind of 2 different ways you can go about this. So one way is to raise both sides as powers of e. So you could say e to the 0 equals e to the natural log of 4 minus X. E to the 0 is 1, and e to the natural log of something is just the something. Alternatively, and it's really kind of the same thing, the other way to kind of think about it is to say, in fact, let me use a new piece of paper here. If I can move this one. another way you can kind of see this would be to say, well, I've got, sorry, forgot what I was writing already. Yeah, 0 equals natural log. The equation I kind of keep in my head to remind myself of how this works is log base 2 of 8 equals 3. There's a logarithmic equation. And remember, when you're taking a logarithm of something, you're really asking the question, this base raised to what power is equal to that number? So 2 to the third equals 8. So when I look at this, this is a reminder of the fact that I can rewrite this as the base to the exponent equals the argument. Well, that's all I'm doing here. My base here that I didn't write is e. And so I can rewrite this as the base to the power is equal to the argument. So that's what's going on. And that's always the relationship between exponential and logarithmic equations. You're welcome. Other questions about that? Make sure my volume's up so I can hear you guys in case you say anything.
Another question.
Yeah.
The last graph.
Mm-hmm.
Why was it on the other side? Like because of the domain, it has to be like less than 4.
Right. So there's a couple ways to look at that as well. You can either think about the domain and say, well, 4 minus x has to be greater than 0, which is going to end up resulting in x being less than 4. But another way to think about it is this graph is going to have a shift to the left of 4, but then it's going to reflect around the y-axis. So if you look at it this, which I know is kind of like, I don't love looking at it that way because it never feels right to me, but you could totally think about y equal to the natural log of 4 minus x. You could also think of it as y equal to the natural log of negative x plus 4. This is a little more kind of, I would say, we're just following the rules to see how it works. I don't like doing it this way, but it is another way to see it. This when you add 4 on the inside, it shifts it 4 to the left, which is that way for you guys, right? Yeah, 4 to the left. So if I did, here's kind of the steps. If I wanted to do it kind of piece by piece. Here's y equals natural log of x, good old normal graph, looks like this. And then I'm going to add 4 on the inside. And when I do that, it's going to shift it left 4. So then I'm going to get this graph where the vertical asymptote to x equal to negative 4. It's going to look like this. And then if I change the x to a negative x, that's going to give me a horizontal reflection across the y-axis. So I do y equal to the natural log of negative x plus 4. The whole graph is going to flip across the y-axis. And so my vertical asymptote here is going to move over to the other side and become the graph that we saw, where now we have a vertical asymptote at x equal to 4, and the whole thing is flipped across the y-axis and looks kind of like that. So that's another way you can do it. I think it's easier to look at the domain, but this is another method that'll still get you there. Yeah, good question. The last thing, not the last thing, the next thing I wanted to do was look at a couple examples of exponential growth and decay. And then I think we'll move on to kind of talking about derivatives of all the things. Because, so as you're probably aware, this class only meets Tuesday, Thursday. So we're going to talk about stuff today, and then you're going to have Friday and Monday class in your actual class where you'll probably get to a lot of things, and then we'll meet again on Tuesday. So I kind of want to prepare you for what you might see on Friday and Monday, right? That seems sensible. Well, let's do a couple examples of exponential growth and decay, and then we'll talk about some derivatives. So let's look at this example to start off with. In 1960, the world population was approximately 3 billion people. And in 2000, the population was approximately 6 billion people. And the question we're going to try and answer is assuming, and this is a big assumption, but it's the assumption we often make, assuming that the world population grows exponentially, what year can we expect the population to hit 9 billion? All right, so when you see these words, assuming the population grows exponentially, or another way of saying this is the rate of growth is proportional to the population size. Those two phrases mean the same thing. They're definitely written differently, right? They are different words, but they actually have the same meaning. If a rate of growth of the population is proportional to the population size, that means that the population is growing exponentially. So when this is the case, we're going to start off by saying, well, our model for growth is y equal to c e to the kt, where c and k are constants that we need to solve for. Typically, C is pretty easy because it's going to be the amount we start off with. So what we're going to do is we're going to make a little table. T for time, Y for population. And I don't want to start with time equal to 1960. That's not a very convenient number. So we're going to say that 1960 is going to be when time equals 0. Usually, if you can, you want to make kind of your initial observation 0, because it's just going to make things nicer. And then we're going to say that the year 2000 is time equal to 40. And at time equal to 0, the population is 3 billion. I'm just going to write 3, so 3 with a lot of zeros. 3 billion if you want. And at time equals 40, the population is 6 billion. And then what we're trying to figure out is what time is it going to be when the population is 9 billion. So I always, when I'm doing an exponential growth or decay kind of problem, I really like making this little table where I write my times and my amounts because it helps me figure out what I know and what I need to know. All right, so now usually you can find C by just saying it's the amount of stuff you have when time equals 0. You can also plug in the numbers. So if I plug these in, I'm going to get, well, Y is going to be 3 billion. And I'm going to get that equal to C times e to the k times 0. Because I'm plugging in 3 billion for Y and 0 for T. K times 0 is 0, e to the 0 is 1. C times 1 is C. So this just gets me that C is equal to 3 billion. And that's typical. C, the constant out there in front, is almost always your initial value. To find the other constant k, we have to use another data point. So we're going to plug in this information now. We say, okay, well, Y is 6 billion, and it's equal to C e to the k times 40. But we also know what C is at this point. So we're going to say, oh, that's going to be 3 billion times e to the k times 40. And that's going to allow us to solve for k. So I'm going to divide both sides by 3 billion. So 6 billion divided by 3 billion equals e to the, it's pretty common to write this as 40 times k instead of k times 40. If you have a number and a constant, we often write the number first, but it doesn't matter. And then 6 billion divided by 3 billion is 2. 2 equals e to the 40k. And then we're going to either rewrite it or take the natural log of both sides. So we're going to get the natural log of 2 equals the natural log of e to the 40k. But the natural log of e to the something is just the something. So we're going to get natural log of 2 equals 40k. Where's that little there? Okay, yeah. And then finally, k is equal to the natural log of 2 divided by 40. I shouldn't say finally because we're not done. So there's our model, or I should say our model for growth is y equals 3 billion times e to the k, which is natural log of 2 over 40 times t. Now you might have learned a different way of doing this in the past. That's also totally fine. Like there's a way of doing it where your base here isn't e, but it's something else. That's totally fine. It's not often the way it's done in the 16 series. In the 17 series, they kind of do this a different way, but this is the 16 series, so we'll do it the way they do it there. So now, of course, I always run out of room before I finish the problem. Like, okay, new page, fine. I hate when I run out of room though. It's like, I love all stuff to be on the same page. So let's do that. So we're gonna take our model now, and we're gonna try and answer the question. So we wanna know, what time is it when the population is 9 billion? All right, well, I'm gonna take my model here and plug in 9 billion for y and solve for t. And really with exponential growth and decay problems, those are kind of the only questions you can usually ask is, how much stuff is there at a certain time? So like if I told you in 20 years, what's the population? Be like, okay, plug in t equals 20, whatever. Or I can ask, what time is it when the population is such a value, right? There's only really kind of, I can either ask how much stuff you've got at a certain time, or what time is it when you've got so much stuff. So plugging in 9 billion for y, we get 9 billion equals 3 billion times e to the natural log of 2 divided by 40 times t. And then we're going to solve for t very similarly to how we solve for k. I'm going to divide both sides by 3 billion. It's going to equal e to the natural log of 2 over 40 times t. 9 billion divided by 3 billion is just 3. And then I'm going to take the natural log of both sides. So I'm going to get the natural log of 3 equal to the natural log of e to all this stuff. And it's going to be a very common practice that when you're going to be like, oh yeah, when I'm taking the natural log of e to all this stuff, the natural log of e to all this stuff is just all the stuff. So we're going to have natural log of 3 equal to the natural log of 2 divided by 40 times t. And to solve this, you could either divide both sides by natural log of 2 over 40, which is going to have fractions and fractions, which I would not recommend. I would rather multiply both sides by 40 and divide both sides by natural log of 2. That's the way I would get to the answer. You can see the work if I write it on the previous step. If I multiply both sides by 40, great, that's going to cancel that. If I divide both sides by natural log of 2, oh yeah, that's going to cancel that. Works out nice. And if you're doing this kind of question on a test, typically you're not allowed to use a calculator, and so this is kind of where you stop. You're like, great, there's the time. It's some number that I don't really know what it is, right? It's like, here's an expression for it. But if you have a calculator and they want a more useful answer, we would get a calculator out and plug it in, and we would get approximately 63. Now, that's not really the answer I want to the question, because the question was, what year is the population going to hit 9 billion people? It's not year 63. It's 63 years after the year we said was time equals 0. We said time equals 0 was 1963. So, oh, sorry, 1960, apologies. I'm already trying to add the 63. So if time equals 63, that's going to be 1960 plus 63 years, which is 2023. Which I don't think we're quite there. I think we're more like about 8 billion people right now. Like I believe, I haven't looked recently, so I don't actually know. Which is definitely one of the downside of an exponential model is it's not always accurate, right? There's a lot of things that are affecting, the growth rate of the population other than just people making more people, right? People are also dying and other things. So it's not a great model for world population growth, but it's an okay-ish model. Since we can't use calculators, we'll be able to solve it all the way out. It really depends on your teacher. So some people might be like, cool, use a calculator. find the answer. But no, if you were not allowed to use a calculator, you would probably be expected to, well, actually, so this would probably not be an excellent answer to the question, because technically I would have to really write the year, which is going to feel kind of weird to say, is going to be 1960 plus whatever this value is here. So it's probably not a great question for a test if you're not able to use a calculator, but this is how you would probably need to answer it on a test if you had to. Usually we try to make it easier to answer. Well, at least I do. I'm not your teacher. They probably will. Sure. So they probably either won't ask, they'll probably ask a question where you don't like have a year you're starting at, but it might be more like bacterial growth instead. Because this answer is kind of totally fine, but having to do this is kind of weird. So yeah. Let's look at one or two more examples, and then we'll start talking about these derivatives. So let's see here. Where'd you go? Other examples. Yeah. One other example. That's fine. So let's look at this one. So TC99M, a radioactive isotope, used in nuclear medicine, has a half-life of approximately 6 hours. Suppose a patient is given a dose of 10 milligrams. How much will remain after 24 hours? So, and then we'll also compare this with how much will remain after 8 hours. So one of these questions is definitely easier to answer than the other one, like a lot easier. The first question is really easy to answer because it's exactly a multiple of a half-life period. So 24 hours is going to be exactly 4 half-lives. So let me ask you all a question. If we're starting at time equals 0 with often we use an amount A for radioactive material, we're starting with 10 grams. After 6 hours, how much are we going to have in the body? Right, 5, because it's a half-life. After another 6 hours, how much are we going to have in the body? 2.5. Or if you prefer, 5/2. After another 6 hours, how much are we going to have in the body? Right. Or 5/4, if you like. And after another 6 hours, we're going to have half of whatever that is, which is, I think, 0.625 or 5/8. So after 24 hours, there's going to be 0.625 grams of this radioactive material in the body. So if the amount of time that passes happens to be an exact multiple of how long your half-life is, it's really easy to answer the question. You'd be like, oh, just half of half of half of half as many times as you need. On the other hand, answering how much there's going to be after 8 hours is not so easy, right? I know it's going to be somewhere between 5 grams and 2.5 grams because I know after 6 hours there's 5 grams left, and after 12 hours there's 2.5 grams left. But that's about as much as I can glean from that without doing more work. So to answer this question, we have to, again, use the model for radioactive growth or decay. Or I should say the model for exponential growth or decay, because it's the same thing. So our model is going to be A equals C to the KT. You can literally use whatever letters you want. People use A, Y, P, and depending on what kind of thing they're talking about, it doesn't really matter. People, and some people use an R here instead of a K. Like if you're talking about, oh gosh, interest compounded continuously, A equals P e to the RT, right? That's the same formula, just using different letters. So here, what's our C value going to be? Well, here's my little chart. I know at time 0, I have 10 grams, and at time 6, I have 5 grams. And I want to know at time 8, how many grams I've got. Well, if I plugged in 0 for T, I would get C equal to 10. Right? C is always going to be that amount you have at time equals 0. You could do the work, right? You could actually plug in 10 for A and 0 for T and solve for C, but it's really probably not necessary. It is necessary to plug things in to find out what K is. So I'm going to plug in the other piece of data and get A is 5. It's equal to 10 e to the K times T, which is 6. And now we solve for K. So divide both sides by 10. You get 1/2 equal to e to the 6K. Take the natural log of both sides. Divide by 6. You guys probably want to see the things. Again, if I'm ever off page, like you can't see what I'm writing, just say something. If you've ever taken chemistry before, you might be familiar with this formula that the K value is natural log of 1/2 divided by the half-life, or the half-life is the natural log of 1/2 divided by the K value. It kind of goes with each other. Some people like to throw in an extra negative sign here. It's not really necessary. So here's our model. A equals 10 times e to the natural log of 1/2 over 6 times T. I will point out that this number here is negative. The natural log of 1/2 divided by 6 is a negative number because the natural log of 1/2 is a negative number. So then to answer the question that we were asked, we want to know how much is it going to be after 8 hours. I'm going to plug in time equal to 8. Most of the time, it's usually easier or less computation intensive to figure out how much stuff there is at a certain time. Because here I'm just going to plug in 8 and get an answer. I'm going to get the amount is 10 times e to the natural log of 1/2 over 6 times 8. And that's kind of it. I could simplify that, I guess, if I really wanted to, and say that's going to be 10 times e to the 8 over 6 reduces to 4/3 times natural log of 1/2. But that's about as simple as I can make that. Oops, sorry, you guys like to see the things. Darn picture-in-picture thing. I'm gonna have to come in here like another day and like practice making this look better. Oh, see, like that's a problem. That's exactly what I was trying to avoid. Okay, now everything, see, I shouldn't have messed with it. It's all wonky now. Okay. Yeah, all right. So that would be the answer I would write if I was asked this question on a test or didn't have get to use a calculator. But if I did get to use a calculator, I would plug it in and I would get approximately 3.97 grams. Okay. Questions? Observations? All right. So order here. Post these notes later. Oh yeah.
Well, I have a question. In lecture yesterday, we took 2 formulas.
Mhm.
Which one was compounded 10 times per year, and the other one was compounded years.
Sure.
What am I supposed to use?
That's an excellent question. So, yeah, there are 2 formulas for interest. So, interest compounded n times per year has the following formula. The amount of money at time t is equal to the principal times 1 plus r over n to the nt power versus interest compounded continuously has this formula, the amount of money at time t is p times e to the rt. And really, you're supposed to use them kind of when the question, basically they're going to tell you in the question, like which one you should be using. So for example, if I said, someone's going to invest $1,000 at an interest rate of 8.5% for 10 years, and interest is going to be compounded monthly. Well, that's definitely implying I need to use this formula. So I should say, how much money is there going to be after 10 years? Well, I would throw all that into my formula, but it's really just putting numbers in a formula. So I'd say, okay, the amount of money after 10 years is going to be my $1,000 times 1 plus, we have to be careful here. It's not 8.5, it's 0.085 because we have to write this as a decimal. So 0.085 divided by, if I'm compounding monthly, what's my n? Right, it's the number of times I'm compounding per year, and there are 12 months in the year. And then it's going to be raised to the 12 times 10 power. And then you would jam that all in a calculator. You get an answer. In fact, just want to see, right, just so we're all clear on how I would do it. The way I would do that. Can you guys see that all right? Maybe. Oh, I can do a thing. Let me. There you can see that. Right. Brighten this a little. Oh, that whoop, okay. No. Well, great. That's just lovely. Tried to make it brighter. You guys can kind of see that though, right? Yeah, okay. So I would start playing, I would probably do it this way. I would do 0.085 divided by 12, add 1, raise it to the 120th power, and then multiply by 1,000. And that's what I'm going to have after 10 years. Approximately $2,332.65. Versus if I was going to compound continuously, we would end up getting 1,000 times e to the r times 10. And then you would, right, to see the difference, we're going to use calculator again. So I'm going to do this way. I'm going to do 0.085 times 10. And then I'm going to do e to the that. Where's my e button? So e to the previous answer. I probably didn't need to do 0.085 times 10 on the calculator, right? That's probably a calculation we didn't need the calculator for. Just got 0.85. And then e to the that's that, and then multiply that by 1,000. Also probably don't really need the calculator for that. And we're going to get approximately $2,339.65. Funny that the cents are about the same. That's atypical. So there's the difference. But really, like, to answer your question, to know what to use, it's usually going to be apparent from the way the question's phrased. Yeah. Now, really, I will say that we don't do a lot of this compounding n times per year. The real point of talking about this formula is because it's kind of a way to talk about how we get the number e. So really, the point of talking about compounding 12 times per year or 365 times per year or some number of times per year is that as the number of times you compound per year increases, the number you're getting closer and closer to is this e value here. So the whole point of this, and I don't want to get too deep into it because it's not like super important. It's a little important, but it's not super important. Oh, want paper? If I could move the papers, maybe. So the point of this, point is the following. That as the number of times you compound gets really, really large, so as n goes to infinity, this expression, 1 plus 1 over n to the nth power, gets closer and closer to e. That's kind of really the whole deal there. So when you have this, I don't want to get too complicated. Or another way of writing it is the limit as n goes to infinity of 1 plus 1 over n to the nth power is e. These mean the same thing, just a different way of writing it. That's kind of really the point of why we talk about compounding interest. It's certainly not the only point. I mean, right, compounding interest is an actual thing that happens in the real world in banks, and there are specific formulas they use that are not just compounding continuously. But it's a nice way of explaining kind of how this becomes what it is. All right, any questions? Let's talk about some derivatives. Yeah. Because I imagine you're definitely going to get to them in the next couple of days here. Sorry, the clock here is really, the clock here says it's 11:50. It's not, it is 9:50, right? That's the time, like that clock is maybe right. Yeah. Okay, like the clocks in all the rooms I've been in lately have been super wrong. So I'm like, okay, what time is it actually? Maybe I just get my phone now. That's the easiest way to see it. Cool. Yes, there's the actual real time I can see. Awesome. So, yeah, let's talk about differentiating things. So, first and foremost, the derivative of e to the x is e to the x. It's a great function. Own derivative, it's super nice. And then, as soon as you use a new rule for derivatives, I kind of automatically want to talk about the chain version of it. So I know the derivative of e to the x is e to the x. The derivative of, say, like e to the x squared plus 3x plus 1 is going to be, so here's the way I think about it. The derivative of e to the x is e to the x. The derivative of e to the stuff is going to be e to the stuff. But then I have to multiply by something because of the chain rule, right? When I say stuff, I'm always thinking back in my head, oh, I need to multiply by the derivative of the stuff. So the derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff. It's very much the same way the chain rule works for anything else. It's the same reason that the derivative of, say, like sine of x cubed plus 5 is going to be, well, I know the derivative of sine of x is what? Cosine of x. So the derivative of sine of x is cosine of x. The derivative of sine of some stuff is cosine of that stuff times, right, the derivative of the stuff. That's always the way the chain rules work. If your thing that's taking the place of x is more complicated than x, I like to call it some stuff, you're always going to have to multiply by its derivative. So for another example, if I was taking the derivative of, say, tangent of sine of x plus 5x to the 4th, I know the derivative tangent of x is secant squared of x. So the derivative tangent of some stuff is going to be secant squared of that stuff, sine x plus 5x to the 4th, times the derivative of that stuff. The derivative of sine of x is cosine of x. The derivative of 5x to the 4th is 20x cubed. So it's the same for any type of function. It's just that this is a new function we're taking the derivative of. So the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of stuff. So for example, if I was to take the derivative of, say, e to the x to the 6th plus cotangent of x, well, I've got e to the stuff. The derivative is e to the stuff times the derivative of the stuff, which is 6x to the 5th The derivative cotangent of x is negative cosecant squared of x. So instead of writing plus negative cosecant squared, let's write minus cosecant squared of x. All right. It's kind of a few different ways we can go here. Sorry, I'm just trying to think about how I really want to do that. Yeah, let's look at the other side of things. Let's also look at taking the derivative of the natural log of x. So there's a couple ways to do this. Yeah, there are a couple ways to do this. So one way is just to say what it is. Seems not very exciting though. The other way is to say, well, I'm really wanting to take the derivative of, yeah, we should talk about it this way because it's kind of interesting. So let's say we have y equal to the natural log of x. The reason I'm doing it this way is because we're going to talk about implicit differentiation, which is something we talked about last quarter. It's going to come back. It's not gone. It's still here. So I really want to take the derivative of this, but I'm pretending like I don't know how. So what we're going to do is we're going to rewrite this as e to the y equal e to the natural log of x. Or e to the y equal to x. All right, I'm going to take the derivative of both sides. What's the derivative of x? Yeah. What's the derivative of e to the y? That's mostly right. Let me ask you a different question. What's the derivative of e to the stuff? Well, the derivative of e to the stuff is e to the stuff. Right. So we're going to get e to the stuff times the derivative of the stuff. And the reason we need that is because y is a function of x, right? It's not just the variable x. So when we have the derivative of e to the y, we really need to multiply by the derivative of the stuff. Well, that's great because we're trying to figure out what y prime is, right? We have y equals natural log of x, and we want to find the derivative of the natural log of x. So we're going to solve for y prime. Y prime is going to be 1 over e to the y. But then we know that e to the y is equal to x. So y prime is 1 over x. Kind of cool. Oops, you guys want to see that? So there's one way you can show that the derivative of the natural log of x is 1 over x. So that's what we've got. The derivative of the natural log of x is 1 over x. Definitely want to memorize that for sure. It's going to come up a lot. I mean, you won't be able to help yourself from memorizing it because you're going to do it so many times. It's just like, yeah, of course. Just like with the exponential function, we should talk about the chain rule version of this derivative. So the natural log of x is 1 over x, and the derivative of the natural log of some stuff is going to be 1 over the stuff. And what do I have to multiply by? The derivative of the stuff. Exactly. Now, I tend to like writing it out like this because I'm really kind of emphasizing the chain rule nature of the problem, right? It's my derivative, 1 over my stuff, and then times the derivative of stuff. But people usually like to simplify this. I would probably rewrite this just to have less space taken up as 6x to the 5th plus 15x squared divided by x to the 6th plus 5x cubed. And there's probably more. You could probably factor out some x's and cancel some stuff. We're not super concerned about that. Yeah.
So basically, the first derivative is 1 over x multiplied by 1.
Right. Yeah. You can totally think of it that way as well. That you're multiplying by the derivative of x, which is just 1. That's a really good way of thinking about it. Let's look at some more examples. Let's say my function. So I should also point out, right? I like writing derivatives like this because it's compact, but it's not the only way I might see it. So let's say our function was the natural log of x to the 4th plus e to the 5x. And we want to take the derivative. So f prime of x is going to be, well, same pattern. the derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff, which is going to be derivative of x to the fourth is 4x cubed. What's the derivative of e to the 5x? Not quite. So what's the derivative of e to the x? Still e to the x. So the derivative of e to the 5x is going to be e to the 5x. But what do I need to multiply by? Right. I have to multiply by the derivative of the stuff. And then if you wanted, you could rewrite this as 4x cubed plus 5e to the 5x over x to the fourth plus e to the 5x. Again, not necessary, but I know people like to write it like this. With some more examples. Let's say our function is the following. G of x is the natural log of x to the 9th power plus the natural log of x to the 9th power plus the natural log of 4e to the x cubed. We could take the derivative of this straight away, right? You don't have to do anything here, but you could do something first. You could use some rules of logarithms to simplify this a little bit. You could rewrite this as, you can't actually do anything with this. This you're stuck with. Natural log of x, all raised to the 9th power. But this one here, you could bring that 9 down in front. You can write this as 9 times the natural log of x. And this one here, you could actually break up as the natural log of 4 plus the natural log of e to the x cubed. And then this would just actually become x cubed. So we could actually rewrite this one more time. It's the natural log of x to the 9th plus 9 times natural log of x plus the natural log of 4 plus x cubed. Notice I haven't taken a derivative yet, right? I'm just rewriting the problem. That's which is why I'm not writing g prime, I'm writing g. So now let's take the derivative. Okay, I have to use the chain rule here. I have some stuff to the 9th power. I know the derivative of x to the 9th is 9x to the 8th. The derivative of stuff to the 9th is 9 times my stuff to the 8th power. And then I have to multiply by the derivative of the stuff. Here, the derivative of 9 times natural log of x is going to be 9 times 1 over x. The next one always throws people off. I like to see people write in the chat, what's the derivative of the natural log of 4? Give you a second. I want to see some answers. You can write me privately. You can write it so everyone can see it. If you're still paying attention in the Zoom lands. Anybody? Guessing you guys are just like, okay. All right, the derivative of natural log of 4 is
1 over 4.
That's, you're close, but not quite. So 1 over 4. So let's say it was 1 over 4. So the derivative of natural log of 4 is 1 over 4 or 1 over my stuff, but then what do I need to multiply by?
By 0.
Right, by 0, by the derivative of the stuff. The easier way to answer this question, though, is to remember that natural log of 4 is a constant. I don't know what it is. It's like about 1.3 or 1.4, I think. But that's a constant, right? It never changes. Plug it into your calculator. It's about 1.38. But it's always about 1.3, right? It's never like something different later on. That number is constant. And its derivative is 0. So, or you could say there's no variables there, right? That's a thing that doesn't change because there aren't any x's. Its derivative is definitely 0. And then the derivative of x cubed is going to be 3x squared. So definitely be careful with the, right, when you see a natural log of a constant, it's really kind of tempting to say the derivative is 1 over the thing because that's what we're so used to. But natural log of a constant is a constant itself, and its derivative is going to be 0. Let's look at some more examples. Okay, let's say we had something like f of x equal to the natural log of x times the square root of x squared minus 1. And you could certainly do this the long way. You could say, I'm not going to write it out, but you could say f prime of x is going to be 1 over the stuff times the derivative of the stuff. But I don't really want to do that, because the derivative of the stuff, I'm going to have to use like the product rule and the chain rule, and it's just more work than I need to do. So when you have the logarithms of things that are complicated, you can make life easier. You can say, well, I'm going to rewrite this. I'm going to say that's the natural log of x plus the natural log of the square root of x squared minus 1. And then I can even make that simpler and say, well, really that's the natural log of x plus the natural log of x squared minus 1 to the 1/2 power. And then I can bring down that 1/2 like that. And now it's going to be much easier to take these derivatives. The derivative of the natural log of x is just 1 over x. The derivative of 1/2 times the natural log of x squared minus 1 is 1/2 times the derivative of that, which is 1 over the stuff times the derivative of the stuff. So simplifying the logarithmic expression before taking its derivative is going to make it easier. And sometimes people like to make these kind of really extra super gross. So let me give you another example of this. Let's say our function was the natural log of, I'll make it extra terrible, the square root of x to the 4th plus 2 times cosine of x over, what do I want at the bottom? X to the 6th times e to the 3x. Oh, yep, thank you so much. Yes. So here's the thing I want to take the derivative of. G of x is equal to the natural log of the square root of x to the 4th plus 2 times cosine x over x to the 6th times e to the 3x. That would be terrible, right? If I actually did like that, 1 over that, and then the derivative of all that, you have to use the quotient rule, the product rule, the chain rule, lots of rules. The point of this is I'm going to simplify it first. So we can simplify by writing this as the natural log of the top minus the natural log of the bottom. So I'm going to write this as the natural log of x to the 4th plus 2 to the 1/2 power instead of the square root times cosine of x minus the natural log of x to the 6th times e to the 3x. And then I can break those apart even further. I can rewrite this as the natural log of x to the 4th plus 2 to the 1/2 plus the natural log of cosine of x minus the natural log of x to the 6th minus the natural log of e to the 3x. Now, why did I write a minus there instead of a plus? Right, because the minus sign here would distribute to both of them. So really, right, this is going to be minus the natural log of x to the 6th plus the natural log of e to the 3x. But then the minus sign distributes. The way I think about it is when you're breaking something like this up into the smaller, easier logarithms, all the pieces on top end up having positive coefficients, and all the pieces on the bottom end up having negative coefficients. It always works out that way. So then one more thing before we start taking the derivative, I want to bring any powers I can down. So I'm going to rewrite this as 1/2 times the natural log of x to the 4th plus 2 plus the natural log of cosine of x minus 6 times the natural log of x minus, I could write this as 3x times the natural log of e, but the natural log of e is just 1. So I'm just going to write this as 3x. And now we've done enough work. Well, we've done all the work we can to make it easy to differentiate this. So now we can actually say that the derivative is going to be, well, let's see. So I'm going to have 1/2 times 1 over the stuff times the derivative of the stuff plus 1 over cosine of x times the derivative of cosine, which is negative sine of x, minus 6 times the derivative of the natural log of x is 1 over x, and minus the derivative of 3x is 3. And then you could probably make this look a little bit nicer by rewriting this as 2x cubed over x to the 4th plus 2, canceling a 2 here and a 2 here. And then this would be minus tangent of x minus 6 over x minus 3. Again, probably not necessary, but if I was trying to type this into web work, I'd probably rather type this than this. So sometimes it's worth simplifying your answers, not because you really need to, but because it's just less terrible to type it than the non-simplified answer. Okay, yeah. Let's see here, let's look at this. Yeah, let's do one of those. So here's what I would say so far about our rules for differentiating. We have kind of 4 things, and we're going to add 4 more to it, but probably not till Tuesday. Just a minute. Are you here for 16B? Okay. So here are our rules so far, or our new rules for derivatives. We know that the derivative of e to the x is e to the x. And we know that the derivative of e to the stuff is e to the stuff times the derivative of the stuff. In a similar way for logarithms, the derivative of the natural log of x is 1 over x. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then, yeah, I think next class we'll talk about there's alternate versions of these where the base is not e. So in fact, we can write them down right now. I feel like we should talk about them before we just write them down. Yeah. So actually, let's go ahead and talk about that real quick. We'll come back to this page in a moment here. So the question I really want to answer now is, what's the derivative of 2 to the x? Well, it's kind of like e to the x, but not quite. There's actually a couple ways you could deal with this. One way is to rewrite it as e to the natural log of 2 to the x. To me, that feels weird. It's not the way I'm used to doing it, but it's totally valid. And then we can write this as the derivative of e to the x times natural log of 2. Or as I would look at it, the derivative of e to the stuff. Okay, what's the derivative of e to the stuff? Well, it's e to the stuff times, right, exactly, times the derivative of the stuff. Which I haven't actually taken yet. I've just written derivative of the stuff. Okay, so here's what we're going to do. We know that this here, that there, that is just 2 to the x, right? It's that, which is that, which is that. Kind of funky, but there's a reason we're saying it. Okay, what's the derivative of x times natural log of 2? It looks complicated. It's not. Let me ask you a different question. What's the derivative of 7x? Say again? Right. What's the derivative of 5x? What's the derivative of a constant times x? The constant. Right? In general, the constant. Okay, what's the derivative of this constant times x? The constant. Natural log of 2. So this is equal to 2 to the x, that part right there, times the natural log of 2. I know it seems kind of like I pulled a trick, right? Like I did some magic and like something happened and I'm like faking you out. But this is actually what the derivative is. Now there's another way to approach it. Let's look at a slightly different example. Let's find the derivative of 3 to the x. I'm going to tell you the answer right now. We're still going to do some work, but the derivative of 3 to the x is 3 to the x times natural log of 3. That's the answer. The derivative of 5 to the x is 5 to the x times natural log of 5. The derivative of anything to the x is that same thing times the natural log of the base. That's the very general rule. But another way of getting here, if you don't like this, I personally don't love this. I think it's kind of weird. The other thing is also kind of weird though. Like there's no good way of getting there. There are just different ways of getting there. So the other way is to say, well, let's let y equal 3 to the x. And I'm going to take the natural log of both sides, with the express purpose of getting that x out of the exponent. So now we're going to bring the x down, and we're going to say the natural log of y equals x times the natural log of 3. All right. So now we're going to take the derivative of both sides. So we're going to take the derivative of the natural log of some stuff equal to the derivative of x times the natural log of 3. All right. What's the derivative of the natural log of some stuff? Exactly, right? We have a rule for it. It's exactly 1 over the stuff times the derivative of stuff. Great. So the derivative of the natural log of y is going to be 1 over y times the derivative of y. Okay. And here's the same question I just asked you before, coming back at you again. What's the derivative of x times a constant? Just the constant. So the derivative of x times natural log of 3 is just the constant natural log of 3. Everybody's favorite constant, right? Natural log of 3, it's my favorite. No, it's not. My favorite to eat. Okay, so now we're going to solve for the derivative. Y prime equals y times natural log of 3. But y is 3 to the x. So we're going to plug this in over here and say, oh, y prime is 3 to the x times the natural log of 3. So when you take the derivative of something with a different base, that's an exponential function, you end up multiplying by the natural log of that base. So to go back to our page with rules on it, the derivative e to the x is e to the x. The derivative of some other base to the x power is that base to the x power times the natural log of that base. I will point out this works for that as well. I could multiply e to the x by the natural log of e, and it wouldn't change anything because the natural log of e is just 1. Excuse me. I think that's probably a good stopping place because it's like 10:18. We're almost out of time. So I imagine you'll talk about this kind of stuff in class on Friday or on Monday, but we will certainly continue here next Tuesday. Yeah. Also, if you have things you want to see next Tuesday, let me know. You can write an email, you can write a discussion, whatever. Yeah, please do fill out the attendance form if you haven't already. For those of you on Canvas, here's a link to it in case you didn't already fill it out, but you can also, for those of you on Zoom, you can also find the link on Canvas if you didn't get it. And I just sent that just to Michelle, so let me actually send it to everybody. There's the link to the class attendance form. Please do fill it out.